So today's lesson is going to be on Hess's Law. And as what's up on the board, with calorimetry, there's problems with certain experiments that are just too slow. We always have an issue with heat loss. Okay, I talked a lot about it yesterday with the combustion calorimetry. Okay? With the regular styrofoam cup liquid calorimetry, if the reaction takes 5 minutes, you're going to lose energy out of that styrofoam cup. Okay? If you have a styrofoam cup with a cup of coffee in it and you look at the temperature difference of your coffee over 5 minutes, there's little temperature change. Okay? But if you leave a coffee on your desk for an hour, it's totally cooled down. So the styrofoam really has limitations over time. Okay? Something like the rusting of iron might take a year to go through 100 grams of iron. There's just no way you could get a delta T with iron. Okay? Hess came up with a way that lets us use multiple reactions that sum up to the one we want to get information with. Okay? And if we can sum up reactions to get that mimics the one we want, then we can get changes in enthalpy for the ones we want. Okay? And it solves not just reactions that are too slow, but that's a big one. Okay? We'll see another solution you kind of solve down below. So this is the heart of Hess's Law. If you like puzzles, you're going to like today. You've got to take equations, flip them, manipulate them, and figure out how you can add them together to get the net that you want. Hess correctly suggested that adding chemical equations, the addition of chemical equations produces a delta H equal to the sum of each of the individual delta H's. If you sum 3 reactions or net together 3 reactions, the delta H of the net is just the addition of each piece. Now, what you really need is a practical example to understand what does that net look like? What does adding them up look like? What are the rules? We're going to work through those. So this will be a bit of an intro slide. The next one will be another intro slide, and then we're going to jump right into practical examples that you'll see me solve. So there's a reaction on the board that we can't actually determine the delta H straight up by itself. Any thoughts of why you couldn't run this reaction exactly as listed? It's going to be impossible. You're going to run into problems if you take pure carbon, add some oxygen, and want to get pure carbon monoxide. Yeah, this is incomplete combustion, and there's no way you're going to get 100% incomplete combustion. You're going to get some carbon dioxide as well as some carbon monoxide. Okay? So you're just never going to be able to do this reaction exactly as is 100%, maybe 50-50. Okay? Hess lets us determine what would the enthalpy change be if this did happen 100%. So we need some reactions that we can run and determine that add together to this net. 2 reactions you can do that sum to that top black one is you can take pure carbon and you can burn it with oxygen and make carbon dioxide. And if you have, this would be complete combustion, make sure there's an excess of oxygen, and you should fully oxidize all of that carbon. Okay? So you can carry out this reaction, determine its change in enthalpy of combustion, okay? Not molar, this is just the end value for 1, 1, and 1, and that is negative 393.5 kilojoules. that gets us our reactants. We got the wrong product, okay? We need another reaction that's going to get rid of this product. So when we net it up, we get the black. Okay? Another reaction you can run is take carbon dioxide and break it down into carbon monoxide and half a unit of oxygen gas. This delta H, that's now one of our reaction types. So I'm just going to put a little R there, generic, where that was a combustion. It's not hydrocarbon combustion, but it's still combustion reacting with oxygen. And this one is 283.0 kilojoules. Okay. And if we look at the net, which is the addition of the two blues, we're actually getting back to the black. This will be a little bit of a recap on doing net reactions. Anything on both sides that has the same chemical, the same amount, the same state, we can cancel. So let's run through all our reactants. Our pure carbon, does that cancel with anything in the blue? No, there's no carbon anywhere, so that's not going to cancel. That's going to come down as one of them. Oxygen, is there any more oxygen somewhere else? Yeah, we've got some oxygen here. They're not the same amount, so we can only cancel the lower amount out of both sides. But it's oxygen in the same state. So this is where it can be handy to put in your ones. There's one oxygen, and we can remove half an oxygen from both sides, subtract half an oxygen from both sides. So all of that oxygen's gone, and I can only subtract away half of that. Okay. No, I'm not showing this on the board. I'm not dividing that by 2. I'm subtracting 0.5 is what I'm doing. I got one carbon dioxide on the product side and one carbon dioxide on the reactant. They're different reactions, so when we net them up, we look at everything on the right and everything on the left. So one CO2 gas, one CO2 gas. Okay? That's not going to show up in a net reaction. So what that leaves is our half a mole of oxygen gas producing our carbon monoxide gas. Okay? The blue summed up to what we wanted. And Hess says if you net up two reactions, you can add up the enthalpies, changes in enthalpies, and that'll be the change in enthalpy for the net. Now this bottom reaction is something with oxygen, so I am going to put that little C. I'm using it for combustion in general, not just hydrocarbon combustion. You add those two together, so this plus that, okay, and you get negative 110.5 kilojoules. Okay. First thing, I'm happy that it's negative. It's a combustion reaction. All combustions are negative, exothermic, so that's a good sign. And we now, if we could run this reaction, we know the energy change. We know the enthalpy change, which is really giving us information of what's the energy in these bonds compared to the energy in those bonds. So that would be the meaning of the enthalpy change. You can actually, we don't do it in regular 30, okay? But it is in the AP curriculum. If you know all the bond energies here, you can add all those up. And if you know all the bond energies there, you can add those up and just look at the difference, and you can make predictions for this. So it's another way other than Hess to make predictions. Okay. Let's look at this graphically, sort of why this is true, and then we're going to jump into examples. On a test or quiz, I'm not going to give you the reactions exactly the way they're going to just nicely add up. That'd be too easy. You're going to get some of the reactions backwards, and you're going to have to flip them. Some of the reactions you might have to double to get the amount of chemical you need, or maybe you'll need to divide them by 2. Okay, and that's where it'll kind of turn into a bit of a puzzle. Okay, graphical, and then we'll get into typical questions. So we've got a chemical potential energy diagram, reaction coordinate on the bottom, I rarely write that out. On quizzes, if you put RC, that's fine on a quiz. On your AP exam, you should write out reaction coordinate. Okay, enthalpy is my responding variable axis, and I've got those two equations that I added together. And I'm going to put the first equation here, and then I'm going to keep going and keep going with the coordination, keep going with the reaction, and flow right into the second one. And we'll kind of get a visual of Hess's law. So the first reaction is pure carbon plus oxygen, and the stoichiometric coefficients do matter. So it's 1 carbon plus 1 oxygen. That's going to produce carbon dioxide. The change in enthalpy is negative, which is why I've already had this going down. And there's 390 some kilojoules released. I did not put the negative because I used the arrow. So that's what that first reaction would look like on a chemical potential energy diagram. Now, if Hess's law, we're summing up multiple reactions. I'm going to put multiple reactions on the same diagram. I'm going to put number 2. I made the 2 red, and I'll do the diagram in red. We start with carbon dioxide in the second one. We already have that. That's where we just finished. So I'm not going to write that again. This reactant is going to be starting at that enthalpy. It's going to make carbon monoxide and half a mole of oxygen gas. The enthalpy is positive. So think, which way am I going to go, down or up? I'm going to go up. Okay, it's endothermic energy out. Sorry, energy in. That extra energy in is why we're going up. Okay, it's going to take energy from the environment. So we're up, and we're up 283. To draw this, I have to notice, okay, that's not as much in magnitude as I went down. So I don't want to go up as much. I want to go up 283.0 kilojoules. Okay. I've not done this to scale. They're relatively, the bigger arrow is bigger, the smaller arrow is smaller, but I didn't scale them. And that's where we got carbon monoxide plus half a unit of O2 gas. If you think of what is the visual of the net reaction, okay, the net, which I'm not going to write out again, but if you sum those two together, that is like going from the very beginning to the very end. I already used 1s and 2s, so I'm going to say A to B. Okay. The net is like going from the very beginning to the very end, which I've called B. Okay. We've got 1 unit of oxygen here and half here. So if you actually do the net, if you take out half an oxygen, you get carbon plus half an oxygen makes carbon monoxide. Okay. What we just solved for in the net is that green arrow. That's that minus 110.5 kilojoules. You're not actually going to do this. Okay. You'll probably not see a test or diploma question like this. If you did, you would know how to deal with it. We don't do it graphically. We do it sort of algebraically in Hess. But this is if you're like, how does that make sense? This visual is trying to make sense of the answer that we got. It's the beginning to end change. Okay. Now, you could add 3 reactions and go through 3 steps and still compare the beginning to the end in Hess. In this course, you'll be limited to, you'll add 2 or 3 together. I'm not going to make you add 5. It would get incredibly difficult and challenging to do. Okay. So now we're actually going to work on the skills that you're going to get tested on. I'm going to do a couple, and then once I feel like you're comfortable, I'm going to stop and ask you to do a couple. First off, what are the rules? They're really just the law of conservation of energy. That is the rules, or that's the basis of the rules. We can flip a reactant for products as long as we flip the sign of delta H. So if a reaction releases 100 joules in one direction, if we flip it, it's going to take in 100 joules. The second thing we can do is just same as baking. If you put double the ingredients in when you bake, you're going to get double the cookies. If you double a chemical reaction, you're going to get double the heat, whether it's out or in. And then you've got a fair bit of data to copy down. So I'll be quiet for a minute or two while you get down. The given equations that are not in the right sequence, we're going to have to manipulate those first two equations to net what's below the red line. That's our goal. Okay, so we have to build what's below the red line. You will always be given a list of equations that you need to manipulate. In my teaching lesson, I'm going to give you equations you need to use. I'm allowed, and Alberta Ed can give you an equation you don't need as a distractor. So you don't have to use them all. Okay? Typically, I only give you one extra, okay? But that's a psychological comment, not a pedagogical one. Okay? The diploma, you might get one extra. Okay? Again, you won't see that right now. Okay? So we've got to build this. So I start with the first reactant. You need systematic tools. So I'm always going to start with the first reactant, and the second, then the third, then the fourth. I've got to go up to my given information and find that reactant. So I need an equation with iron, that is iron 3 oxide, and there it is. Okay? That's what I want. Okay? Is it on the side I want it? No. I can manipulate that equation. First rule is that I'm allowed to flip it as long as I flip the sign of delta H. If it was endothermic in one way, it becomes exo, or vice versa. So I'm going to write this in the reverse sequence. Fe2O3 solid. Now I like to keep my arrows in the middle. I left space here so I can always write two reactants and then two products. Okay, you don't have to, but it really helps to line your arrows up. So now I'm going to put the reactants are going to be products. Okay. Now we're getting to a choice, and you're going to have to follow my choice. I prefer decimals than fractions. Do we have any fraction lovers? Good. You can do this in fractions if you want. My brain prefers to cancel 1.5 with 2.5, then 2/3 with 7/2. Okay? Both work. Both are mathematically true. I just prefer to write that 3/2 as 1.5. Most students, their brains are a little better with the decimals. Okay? So I will always take the fraction when it's given to me on a test question or a homework question and convert it. So 1.5 O2 and the delta H. Okay, these are all going to be standard. So I'm putting the knots in. Let's see, was minus 824. So it's now going to be positive 824.2 kilojoules. Okay. Technically, you don't have to put positives. I want you to put the positives. Remind yourself that it is endothermic. Okay. So I have got that reactant. Now, often you get something else you need. Is there anything in this black reaction that we also wanted? Yeah, we got the iron that we wanted. So that's been done for us. Okay. After I get the chemical, I ask, do I have the right amount? Okay. And in this case, I do have the right amount. I wanted one of those and I got one of those. So I don't have to double this or triple it or cut it in half. Okay. I do want to kind of get through this whole first one, and then I'll take more questions on the second one. Okay. So then systematically, I move to the next reactant. Okay. I'm just going to work my way across so I have everything. That one requires solid elemental aluminum, which I have in the first equation. So I want it as a reactant, I have it as a reactant, so I'm going to pull it down exactly as listed. 2 aluminum solid plus, again, I'm getting rid of fractions, I'm turning them to decimals, 1.5 O2 gas. I've nicely left room to line up my arrows. And I get Al2 aluminum oxide. I didn't do anything here, so I can copy that enthalpy change exactly as written, minus 1,675.7 kilojoules. I always bring it down and then ask myself, is it the correct amount? And again, I don't have to scale it. I wanted 2 units, 2 moles. This gave me 2 moles, so I don't have to double or half or anything. That gave me my aluminum that I wanted. It also gave me my aluminum oxide. So I have all 4 pieces now. This should cancel and work out for me. Same as in balancing, you don't actually sort of balance you normally balance most elements and the last one just works out for you. You get the same thing in Hess. You find 3 of the 4 pieces and the last one just comes with the last piece. I can cancel anything on both sides. I've got 1.5 oxygen reactant, 1.5 oxygen product, 1.5 reactant. I can cancel those out. And I have my iron oxide, my 2 aluminum, my 2 iron, and my 1 aluminum oxide. I'm just not going to write that out again. We have it written there already. Okay? But what I do want to do is determine this delta H. Okay? The delta H for this reaction under standard conditions, because those are under standard conditions, is just the sum of these. This plus that. You just have to be really careful if you're negatives. Okay? And as grade 12s, you're probably all used to, you can put a subtraction in for a negative on a graphing calculator. You'll get that error. So sometimes even I do that by mistake. And you're like, why am I getting this error? It's because you put a negative in for subtraction. So you get negative 851.5 kilojoules. Okay. We just completed Hess's law. Now, I like to do the first one without pausing for questions. I'll take them, move on to the second one, and you can stop me on the second one in the middle. Do you still have a question? Yeah, it would. Yeah, it would technically be a decomposition. Yeah, I didn't bother writing the letters out and thinking about it. I left out those letters, but it would be, if it's a formation, that would be a D. Second one, I'll do probably 3 at the most. Again, you have a list of given equations, and then you have the one you want to solve for. You could skip the words at the top. Okay. You're given a formation reaction, 2 formation reactions, and a water plus pure carbon makes carbon monoxide and hydrogen gas is what we want to solve for, which is equation number 1. So I always start, okay, you can take shortcuts, but I always teach it. If you want a nice systematic approach, start with the first reactant, which is water, gas. The states matter, so you could not grab liquid water. That could be a distractor equation that you would have to ignore. Okay, water, gas, that is in the second equation, okay, but it's on the wrong side. I'm going to flip it. 2 H2O gas produces 2 hydrogen gas molecules plus 1 oxygen gas. I flipped it. That's the bottom one, so that's now positive 483.6 kilojoules. I always like to get the equation down and then ask myself, do I have the proper amount? And I don't. I want 1 water. There's no number in front, but the equation had 2. So just like baking, you scale recipes up or down. I'm going to divide this whole reaction by 2. Divide by 2, and that will get the amount that I want. You can only multiply or divide reactions. When we net, we add or subtract. When we scale, we divide. So 2 divided by 2 is 1. 2 divided by 2 is 1. There's no number here, so there was a 1. I divide that by 2, and I get 0.5. And then at the very end, I'm going to divide that by 2. I always just go divide by 2 and then just do all this math on my calculator at the very end. Okay? You could obviously do this right away and write it in if you want. So that gets me my water. Doesn't get me my carbon, doesn't get me my carbon monoxide, but it does get me my hydrogen, and in the right amount. So I need to get pure carbon, which is there. It's on the proper side, so I'm going to pull that down exactly as is. 2 solid carbon plus oxygen gas produces 2 carbon monoxide. I didn't flip this or do anything to it, and it's that one. It is super easy to go and look up and grab the wrong delta H. I've done it occasionally. I try to go slow and not do it, and I've seen lots of students, you do everything right, but you go up and you grab the wrong delta H and pull it down, particularly if there's 3 or 4 of them here. Just be really careful with that step. Okay. Same as before, I want 1 carbon, but the equation gave me 2. So I have to divide that by 2, the whole green equation. So 2 divided by 2 is 1. 1 of those divided by 2 is a half. 2 divided by 2 is 1, and I have to cut the enthalpy in half. Okay? Law of conservation of mass and energy. Okay? Half the mass is reacting, you're going to get half the energy change. That gets me my 1 pure carbon and gets me my 1 carbon monoxide. I do have oxygen gas all over the place that I don't want, but it's the same amount on both sides. Half O2 gas, half O2 gas, that cancels. Okay. What's left is the net that I want. I'm not going to bother netting this up because I've checked, I've got the 4 pieces with the right stoichiometric coefficient, so I can predict the delta H for this reaction. Okay. I didn't write this one down, so I'm going to need somebody to help me. What is this algebra, the top plus the bottom? It's going to be 31.0. What is the sign? So we had some flipping and we had some scaling in this one. Okay. This is as hard as it gets, except for there wasn't an extra distractor equation. Okay. I guess it would be harder if you had to add 3. Hopefully you've seen me do the skills, you've seen me flip, okay, you know what to do there, you've seen me scale it up or down, you've seen my approach, systematically work your way through. You tend to get 2 chemicals at a time when you pull an equation. That's not a law, that's just a trend. No, you might have to like divide by 2, which is the same as multiplying by half. So yeah, you could multiply by half, but I'd call that dividing by 2. So I'm not sure where that leaves your question, but no. Yeah, you're not going to have to do weird fractions. In theory, you could. There's nothing against the law of conservation of mass or energy that says you couldn't multiply by 1/7. Okay? Practically, it doesn't help us get where we want to go. Okay? I'd like you to try this next one. Okay? So you don't have to write it all down. You could look at this equation, start grabbing pieces. Can you build up equation number 2, which I've put in a box? So this 2 in front is equation 2. It's not a number. It's not 2 carbon dioxide. It's equation 2 starting with, with carbon monoxide. Can you use, you might need all 3. You may not need all 3. So again, when you finish that problem in your textbook, 1, 3, 5, and 9, there are some workbook Hess's Law practice also. One possible way to break this up is to do the textbook practice now, and when you're studying for quizzes and exams, you could go back and do those workbook ones. Okay. Number 9 is a bit tricky. You don't have all the equations written out for you. Okay. I could give you the molar enthalpy of combustion is this, make you write the equation and the delta H and then do Hess's Law with it. So 9, you've got all those communicating enthalpy skills. Okay. We're going to do lab 11.3 in 45 minutes. Okay. So it's on page 517. Okay. So I'd like you, I wrote out the purpose, but I'd like you to fill in the problem hypothesis, which would be the correct answer. And I'll talk about this in a little bit, but I'd like you to do the Hess's Law, even though you don't know the numbers yet. Okay? In your book, you'll see there's 3 equations you need to manipulate and do Hess's Law with. The values for delta H aren't in the book because you're going to go figure them out in the lab. Okay? But I'd like you in your prediction to figure out the first equation that's given to you. Are you going to flip it? Are you going to double it? What are you going to do to it? Okay? But again, you don't have the number. Okay? So you can't do the number part of Hess's Law in your prediction, but you can do the equation flipping and rearranging, okay? Which is saving you some analysis. Okay? Again, read through the lab and then I'll put some stuff on the board, but I don't want to say more until you've read it. What I say isn't going to help your understanding. Okay? So I'm going to leave it on the questions. I will scroll down to the pre-lab in 5 minutes or so.